As the 20th century came to a close, two independent teams of astronomers employed telescopes around the Earth and observatories in space to study supernovae in distant galaxies. Each team sought to measure how gravity was slowing the expansion of the universe. They made a shocking revelation. The expansion was speeding up, and an unknown force was behind it. The 20th century birthed the physics revolution.
We've worked for a century to test it. Einstein's relativity is holding up.
Scientists are unraveling the Big Bang
It's an explosion of space itself.
and asking new questions of our cosmos.
We're still not entirely sure how supermassive black holes form, but we've been able to detect that they exist in pretty much every galaxy.
New instruments are confirming old theories.
It has taken about 50 years for us to build an instrument that's capable of registering gravitational waves.
And shedding light on the ultimate fate of the universe.
We may be sailing off on an infinite journey of expansion.
With each piece of the puzzle, the mysteries deepen.
We have defined the boundaries of our ignorance, and that's a very exciting place to be as a scientist.
Humankind has forever sought to understand the forces that govern the heavens and the world around us. Generation after generation, ideas were proposed, tested, revised. The shoulders of giants grew tall, building a vantage point with which to see reality. In the 17th century, an English polymath assigned mathematical theory to his observations.
Newtonian physics was a revelation. It changed the separation between humanity and the cosmos and revealed not just that we were connected, but that we could understand it.
Isaac Newton published the first volume of his Principia Mathematica in July 1687. Within its pages, he detailed an equation for gravitational attraction. Everything in the universe pulls on everything else. Particles of matter attract each other with a force directly proportional to their masses and inversely proportional to the square of the distance between them.
We were able to predict accurately where planets were going to be in the future, where they were in the past. We were able to find planets through the perturbations of that planet on another one.
After William Herschel discovered Uranus in 1781, astronomers noted its curious path across the sky. Employing Newton's version of gravity, the planet's motion seemed to be influenced by a distant body.
European astronomers and mathematicians got together and they calculated that if there was an existing planet outside of Uranus, then this would explain these funny movements.
Two astronomers working independently each calculated the hypothetical planet's location in the night sky. A third trained his telescope toward that position. Collectively, they discovered Neptune. But there was one planet which refused to play by Newton's rules: Mercury. Tracing Mercury's orbits, its closest point to the Sun, its perihelion, moves ever so slightly every single year. The phenomenon is known as precession.
Mercury's orbit never quite fit correctly with the classical model.
It could not possibly be explained with Newton's law of gravity after we had observed it and seen the perihelion advance.
One hypothesis, there had to be another planet even closer to the Sun, perturbing Mercury's orbit. The mystery planet was christened Vulcan after the Roman god of the forge. While some hunted for Vulcan, others sought a new mathematical theory to explain Mercury's strange behavior. In 1915, a German physicist presented a new take on gravity.
Einstein's relativity absolutely transformed the way we think about the universe.
To step out of this classical world of gravitation and be able to just turn that completely upside down and be able to come up with a mathematical formula, which is actually quite simple.
General relativity treats space as deformable. Mass, from a grain of sand to the entire Earth, bends space. And all natural bodies moving through the universe will follow those curves. The Sun doesn't pull on the Earth. The Sun sits at the bottom of a gravitational well, and the Earth falls around it, traveling just fast enough that it doesn't spiral inward.
In relativity, we saw a sweeping away of the old and ushering in of a new paradigm.
Applying the novel equations of general relativity, Mercury's quizzical orbit was finally explained, and its precession accounted for. Vulcan was no longer necessary. However, Einstein's theory would need a further demonstration to supplant Newton's work, which had reigned supreme for over 200 years.
Einstein had predicted the presence of a massive object would bend the way light passed through space.
An upcoming solar eclipse was set to darken the southern Atlantic on May 29, 1919. A team of astronomers, led by Arthur Eddington, seized the opportunity to test Einstein's theory.
The Eddington mission in 1919 was to measure the deflection of a star's light as it passed close to the Sun.
If Einstein was correct, a group of stars would appear in a slightly different part of the sky, their light perturbed by the Sun's gravity as it passed in front.
In 1919, the eclipse was special because this eclipse happened projected against the background of the so-called Hyades star cluster, a small concentration of stars that were the best studied stars to date.
A first base of observation was established in Brazil, and Eddington positioned himself on an island off the coast of West Africa. The moon's shadow charged across the Atlantic. Each station only had minutes to capture the eclipse on photographic plates. Returning to England, both teams announced their findings. Einstein was right.
This experiment was incredibly successful, and the deviations in the positions absolutely confirmed Einstein's predictions.
Scientists have continued putting general relativity to the test. It keeps passing.
For several centuries, we've worked with Newton's gravity. Then came along Einstein with relativity and showed that in certain extreme situations, Newton's gravity doesn't really work well.
Einstein was able to explain all of everything we saw. Even to this day, we've still not been able to go against his theories of gravity.
Now, is Einstein's relativity the final answer? We've worked for a century to test it. Einstein's relativity is holding up. Precisely. I find that astonishing.
It all came back to a simple desire to understand and have a more complete picture of our universe.
While we can still use Newtonian mechanics in our day-to-day lives, Einstein's revolutionary notion of gravity is required to understand the universe.
We need to look out to places where we have extreme densities, temperatures, and things are very dynamic. That's where we will really be able to refine our ultimate theory of gravity.
To study the heavens, astronomers capture light in telescopes. That light is composed of a spectrum of colors.
We can understand the fundamental makeup and dynamics of something by taking its light and splitting it up into its component colors.
Unique to each object, this combination of colors represents the chemical fingerprints of astronomical phenomena. But to understand how a star or a planet could have such a fingerprint, scientists needed to surpass the classical understanding of the universe. They needed to reconceptualize the very concept of matter. The ancient Greeks envisioned the atom as indivisible, the most fundamental building block of substance. In the 19th century, scientists discovered it was far more complex.
As our ways to study materials advanced in the past 200 years, the structure of the atom is no longer just one homogeneous thing, which is the smallest thing in the world.
The atom was instead demonstrated to be comprised of several components, a nucleus where most of the mass was contained, with an electron that would orbit around.
But according to classical Newtonian physics, the electrons in a planetary model would spiral down toward the nucleus, destroying every atom in existence. In 1913, the Danish physicist Niels Bohr introduced his model of the atom. The model relied on a new explanation of reality that had recently been developed: quantum physics.
Quantum physics is the idea that nature is divided into discrete but very much differentiated bits.
It's trying to explain the very smallest scales of the universe.
The tiny bits of atoms and how they behave, the weirdness and behavior of chemicals, and basically every tiny thing in our universe.
In this re-envisioned universe, electrons are forced to orbit around their nucleus at precise distances, like rungs on an unevenly spaced ladder. The size of those rungs dictates the exact colors of light an atom can absorb or emit. Each element has its own arrangement.
We have a very outstanding challenge in trying to visualize and explain what the quantum world actually is.
For decades, astronomers had been cataloging stars based on the missing colors in their rainbow of light, what they called spectra, and matching the missing colors to certain elements.
If we look at a spectrum and we see certain wavelengths missing, we can tell which element in the star was responsible for absorbing that light.
Scientists could utilize spectra to identify chemical compounds throughout the cosmos.
The ghosts of unimaginably distant objects like quasars and pulsars can be made to tell their stories by manipulating the light that they emit.
In the 1920s, quantum physics evolved. The particles within an atom were revealed to also act like waves.
The electron is not in a position around the atom, it is rather spread out. There is a cloud of possible locations.
The universe became uncertain, and that uncertainty helped solve a long-standing mystery of how our sun was able to shine. Under classical physics, hydrogen nuclei in our sun's core can't get close enough for long enough to undergo fusion. It simply isn't hot enough. But under quantum physics, hydrogen clouds can. The chance of fusion is astronomically tiny, but it's enough. Combined, the theories of relativity and quantum physics have allowed us to explain the intricacies of the universe. But employed in tandem, they failed to provide any answers.
These are two theories of the way things behave which are mutually exclusive. They don't sit together, and yet they both work very, very well.
When we try and describe big things with quantum mechanics, it makes no sense. When we try and describe small things with general relativity, that doesn't work either.
Gravity, as we currently understand it, cannot operate within a quantum realm.
There must be a theory out there that we haven't grasped yet.
Maybe it's a new law of physics, maybe it's tweaks to these laws, and maybe it's something else.
Without a unified theory, we'll never be able to truly comprehend the beginnings of our universe. 13.8 billion years ago, reality as we know it was born.
All of the material that forms our universe at a single point. That's the Big Bang.
An infinitesimal spark became an infinite cosmos.
It's not so much an explosion into space, it's an explosion of space itself.
As the universe grew to an unfathomable size, stars began to shine and galaxies coalesced. Modern technology allows us to observe many of these moments, but not the earliest points of our universe's history. As we turn back the clock, a cosmic barrier arises 380,000 years after the Big Bang.
Before that moment, in the first few 100,000 years, our universe was so hot and dense, atoms were ionized and they were a plasma.
Any radiation a particle emitted would immediately be absorbed by another.
And it acted like a fog. There was no way for the light to travel.
It wasn't until the universe had expanded and cooled sufficiently that that radiation could start flowing freely.
The atoms recombine, the fog clears, and the light travels to us, and has traveled towards us essentially unimpeded since that moment.
The oldest light is known as the cosmic microwave background. It wasn't discovered with our eyes, but rather our ears. In 1964, two astronomers at Bell Laboratories were testing their radio equipment, but something was interfering with the signal.
Maybe it was caused by something in the Earth's atmosphere, and they spent a long time trying to remove it from their data.
They went to all sorts of lengths to account for and remove the effects of this static.
They thought it was actually bird poop they were looking at and had to clean it out because pigeons nested in their telescope.
They didn't call it bird poo in the paper that they published, they called it a white dielectric material.
They had no idea what was causing it. It wasn't clearly coming from anything that we knew. And it was actually called Little Green Men for quite a while because, what else could it be?
They were able to talk to a physicist, Hans Bethe, who had some understanding of what might be going on, and they were able ultimately to conclude that the static that they were hearing was actually the cosmic microwave background, the relic radiation from the Big Bang.
Over the decades, space-based observatories have mapped this signal, which exists everywhere in the sky with eerie uniformity.
One of the very earliest measurements was made by a satellite observatory called COBE, the Cosmic Background Explorer. It made an incredibly famous measurement of the temperature of the microwave background. It is one of the most precise, most pristine measurements in all of astronomy, maybe in all of science.
The remnant heat of the Big Bang was predicted to be a few degrees above the coldest possible temperature, roughly minus 270 degrees Celsius. The COBE mission confirmed that prediction. Our universe had a beginning and had been expanding ever since.
The cosmic microwave background is actually pretty constant all over the universe. It implies that it was all produced in the same place. And this is what enabled the cosmic microwave background experiments to confirm the Big Bang theory.
Following COBE, further missions exposed hidden structures of an infant universe where gravity could act to form stars, galaxies, and the Earth itself. However, all that we've learned from the cosmic microwave background only takes us so far back, the 380,000-year barrier. Any earlier, and we have to rely on scientific theories and models.
We can use Einstein's relativity to work our way back in time. Quantum physics also comes in to describe how the particles would interact in this universe, which becomes amazingly small and amazingly concentrated.
But at the earliest moments, when all cosmic energy was contained in a nearly infinitesimal point, theory fails us.
A tiny fraction of a microsecond away from the Big Bang, our equations actually break down. We don't have a theory that works all the way into this extreme regime.
Beyond our beginnings, there are other places throughout the universe where physics appears to be broken. The most extreme objects in our universe are invisible.
A black hole is a region of space-time which is so dense and has such strong curvature that nothing, including light, can escape from it.
Fundamentally, it's what happens at the end of the lifetime of a very, very massive star.
For the largest stars, life ultimately ends with a gravitational implosion, a supernova.
The mass that's left behind won't have any fuel to sustain it. It all crumples together into an infinitesimal point.
A black hole. There is no surface, only an edge past which you could never retreat, trapped for eternity.
The idea of a hole is very apt. You would look up and the universe that you had just left would be an ever narrowing well of light above you.
The notion emerged from Einstein's equations. However, black holes spent decades as mere mathematical oddities, not real-world phenomena. In 1971, astronomers identified an intense X-ray source dubbed Cygnus X1. It lined up almost perfectly with a known star, but the star was incapable of generating those X-rays. By 1973, a consensus had been reached. The star was orbiting a black hole. The very next year, a source of intense radio waves was identified in the heart of the Milky Way. The phenomenon, Sagittarius A star, was best explained by the presence of a black hole. It is not the black hole itself that emits the radio waves, but matter in a disk surrounding it, spiraling downward.
As it gets ever closer to the black hole, its orbital speed increases and eventually becomes close to the speed of light. In doing so, it's constantly bumping, jostling against its neighbors. It is a tremendous amount of warmth, of heat, of light.
While Sagittarius A star itself could not be resolved by our telescopes, astronomers could spy on its stellar neighbors.
We've been able to measure its presence and we've been able to measure its mass, not because we can see it directly, but because we can measure its gravitational influence on the stars that orbit very close to it.
The black hole at the center of our galaxy has a mass roughly 4 million times that of our Sun.
There is a particular breed of black hole that we call the supermassive black holes.
Most galaxies, if not all galaxies, contain at their very centers a supermassive black hole.
So some of the biggest galaxies have black holes in them with 20 or 30 billion times the mass of the Sun, which is astonishing.
We're still not entirely sure how supermassive black holes form, but we've been able to detect that they exist in pretty much every galaxy.
While indirect data suggested black holes were a part of our reality, capturing visual evidence seemed nearly impossible. Because radio wavelengths are the longest amongst all types of light, they require much larger telescopes to capture. To image a supermassive black hole in another galaxy would require a radio telescope as big as our planet.
We'd love to build a telescope the size of the Earth, but we can't do that.
Nevertheless, humanity accepted the challenge. An international collaboration of organizations and observatories combined their efforts to birth the Event Horizon Telescope.
We use several telescopes sited around the world, and we use them as a team to make a really good picture.
You have large radio telescopes that are situated in varying places on the planet. You can combine those signals and you can simulate a radio dish, which is the physical size of those separations.
Beginning with 3 observatories in 2009 and expanding to 8 by 2017, the Event Horizon Telescope set its sights on the center of Messier 87, a galaxy 55 million light-years from Earth. The data collected by each telescope was fed into a supercomputer.
Each individual telescope, its story is combined with the others in this computer to create one incredible, clear, revealing picture.
When the images were finally processed, they did not expose the black hole itself, but rather its shadow, measuring 100 billion kilometers in diameter. Nestled within a supermassive black hole 6.5 billion times more massive than our Sun.
We see at a region where time stops. This is a very different part of the universe that we're seeing for the very first time.
While scientists cannot explain the intricacies of black holes until we find a theory that unites physics, they have developed new methods to study them. Waves of light are not the only ripples that traverse the cosmos. According to general relativity, space itself can also ripple. Gravitational waves are caused by mass accelerating through space.
Einstein first predicted gravitational waves in 1916, but the size of these waves was going to be so small that he never thought they would be detected.
Only the most extreme events in the universe create measurable gravitational waves.
When it got to the point that black holes were no longer ridiculed, the physicists started saying, maybe we can really seriously think now about building a detector.
We would need a laboratory capable of isolating distortions of space smaller than an atom.
It has taken about 50 years for us to build an instrument that's capable of registering gravitational waves, the shaking of space itself.
In 2002, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, began its search for evidence to support Einstein's proposition.
We detect gravitational waves using instruments called interferometers. They're shaped like an L. We shine a laser from the center of the L down the two arms.
After traveling 4 kilometers down either arm, the laser light strikes a mirror and returns.
The principle is that if a gravitational wave is coming from out in space and passes into the detector, then it will alternately stretch one arm and then the other arm. And we'll see this in the interference pattern of the laser beams when they're recombined.
To ensure a signal is genuine, LIGO built 2 detectors on opposite sides of the United States. Both stations were silent for years, but following an extensive refit, a signal was detected. When 2 black holes orbit around each other, they lose energy by the emission of gravitational waves. They enter a death spiral, orbiting faster until they collide.
Ladies and gentlemen, we have detected gravitational waves. We did it.
Einstein's theory dictated the event, and both LIGO signals matched it. We detected the merger of 2 black holes, a collision 1.3 billion years old.
Once we had the first one, it became obvious that we were going to get more and more of them as we increased the sensitivity of the detectors.
LIGO witnessed another type of collision 2 years later.
The second really major detection for LIGO was a binary neutron-star collision. When they collide, they give off all kinds of signals.
Unlike a black hole merger, a neutron-star collision could be witnessed not just with a gravitational wave detector, but optical telescopes as well.
We were fortunate to be able to localize the area in the sky for that signal to a very small patch. We sent it out to the astronomers, and this created an unprecedented avalanche of telescope satellites around the world, redirecting their programs of observing. That had a flow-on effect. Everybody could image it in radio, X-ray, and so on. And this gave us an enormous amount of physics that we didn't previously have.
Humanity entered an era of multi-messenger astronomy, studying the same object using a combination of information sources and employing multiple phenomena to confirm, enhance, or contradict our previous notions of the universe.
Whether it's radio waves, light you can see with your eyes, X-rays, it requires a light particle that travels through space. If we are wrong about our view of light, everything in our universe is essentially wrong. So gravitational waves offer an independent way of measuring the universe.
It gives you a holistic picture of what is actually going on out there. The more messengers you can use, the better informed you are about how the universe works.
Messengers that come from traditional ways of viewing the sky, that come from particles, using all of the available information.
That is how astronomy is progressing, and big collaborations are being formed between specialists in the different disciplines. It's a bright future for astronomy.
More powerful gravitational wave detectors could reveal the earliest moments in the cosmos. While the oldest light takes us no further than 380,000 years after the Big Bang, the oldest gravitational waves would reveal our history up until a tiny fraction of a second after the universe's creation.
I look forward to that with great interest because it may turn out that we've got it all wrong. And when we look at the gravitational waves, perhaps they'll tell us a different story from what we're expecting.
In the 1920s, humanity realized that our Milky Way galaxy was just one of many, millions and even billions of light years away. Other galaxies nested together in clusters, slowly rotating around one another. A decade later, Swiss astronomer Fritz Zwicky had a mystery on his hands. He had been observing the Coma Cluster, a group of over 1,000 galaxies stretching 10 million light-years across. Given their collective mass and gravitational influence, some of the galaxies were moving so fast that they should have broken free.
The gravity from the galaxies that we see is not enough. There must be more gravity to allow the cluster to hold together. Otherwise, the galaxies would have actually whizzed off into space and we wouldn't have clusters anymore.
Several decades later, studies of individual galaxies posed the same problem. Just as all the bodies in our solar system orbit a central point, all the stellar systems, gas and dust in a galaxy rotates around the galactic core. In the 1960s, Vera Rubin and Kent Ford began charting these rotation rates, measuring how fast material within a galaxy spun relative to its distance from the center. Spinning matter in our universe operates under a principle known as conservation of angular momentum. The total amount of mass and the distribution of that mass dictates how quickly an object will rotate.
You could do this right now. You could spin around in your desk chair and test it that as you move your arms out, you slow down, and as you move your arms in, you speed up.
Planets in our solar system are rotating exactly based on gravity, based on the sun's mass and the mass of the planets.
But instead of slowing down at the outer edge of a galaxy, Rubin noticed that these stars moved just as fast as those much closer in.
Vera Rubin showed that the stars in a galaxy are not rotating like the planets in our solar system. They're rotating as if there's much more matter than we can see in the galaxy.
And so either our laws of physics are wrong, but they kind of work in every other case, or there's another type of mass that we've never discovered.
Zwicky called this invisible matter Dunkel Materie. We know it today as dark matter.
We call it dark matter because it doesn't emit light and it doesn't absorb light at all. So the only way it interacts with other material is via gravity.
Dark matter forms huge structures across the universe, existing as gravitational scaffolding. We see its effects in photographs. Looking at galaxy clusters, the dark matter will distort the images of any galaxies behind it. This effect is known as gravitational lensing.
The gravitational lensing is a really awesome effect in the universe where if you have a massive object, the light will get bent around, just like a magnifying glass or like a refracting telescope. That magnifies the light of the background galaxy and distorts it.
After accounting for the lensing caused by regular matter, astronomers can map the distribution and concentration of dark matter. At current measurements, it appears to be 5 times more abundant than all visible matter.
There is a lot of mass out there in the universe that we just cannot see with our eyes that doesn't emit light, but interacts in every other way we measure it.
Scientists continue to hunt for an explanation of dark matter.
Dark matter could be made of particles that we haven't yet discovered. And we're looking in places like the Large Hadron Collider, smashing particles together with high energy to try and spew out these amazing particles that perhaps we haven't discovered.
One hypothetical type of dark matter could be detected by studying neutrinos, the smallest and least interactive particles known to physics.
So neutrinos are the awkward cousin in the family. If dark matter is another type of particle that we haven't seen, as dark matter collides with itself, It should give off neutrinos that can travel through space, that we can see here on Earth, that we can measure and collect in a lab.
Neutrinos are in the same family of subatomic particles as electrons, but they have no charge. They're cosmic ghosts, interacting with matter so irregularly that trillions of them are streaming through your body this very moment.
There are some intriguing suggestions that come actually from deep underground experiments where you build particle physics detectors which are seeing things that can easily pass through the Earth.
We go to the bottom of mines or underneath mountains to use the rock above as a shield so that we can have a better chance of seeing this rare collision with our detector.
The internationally funded IceCube experiment at the South Pole is the largest neutrino detector in the world. A cubic kilometer in size, buried over 2 kilometers below the Antarctic ice, turning 1 billion tons of naturally frozen water into its own personal neutrino catcher. Across 2 years, IceCube indirectly detected 28 neutrinos. However, none were attributed to dark matter.
Experiments of that kind have given some weird hints that just maybe we might be getting close to finding whatever particle it is that makes up dark matter.
Meanwhile, NASA's Fermi Space Telescope hunts for the signatures of dark matter from low Earth orbit.
We think that a type of dark matter forms antimatter and matter, and it can form and then collide together and annihilate itself.
Such an annihilation would create gamma radiation, which Fermi is designed to detect.
So far hasn't detected them, but it's getting very close now.
Until scientists find solid evidence, the lack of detections constrain the possibilities of what dark matter could be. We're narrowing the search field.
Another possibility is that dark matter could not exist. It could be that we've just got the maths wrong, and that's perhaps even more intriguing and even more worrying.
However, another search for the invisible leads to an even larger mystery. It was astronomer Edwin Hubble who revealed to the world that our galaxy was just one of billions in 1924. Less than a decade later, he announced another revelation. The universe was not constant in size. It was expanding. Over the decades, astronomers settled upon the Big Bang theory, and that the expansion set forth at our origins would slow under the power of gravity.
The expansion of the universe originated in the Big Bang, but everybody thought that because the universe is full of matter, galaxies would, by their mutual gravitational pull, slow down the expansion.
Eventually, the universe would begin to collapse. The race was on to calculate when.
People were trying to set out how fast the universe was slowing down. When was the universe going to stop and collapse back on itself?
In the 1990s, 2 international teams began measuring the expansion, utilizing some of the brightest phenomena in the known universe. Type 1a supernovae. The teams compared the age of particular supernovae with how quickly they were moving away from Earth. By 1997, the teams had collected a wealth of data, stretching back to half the age of the cosmos. The next year, they went public with their conclusions, with a result that defied the known laws of physics.
The universe is not slowing down in its expansion. It is accelerating. And it seemed for a while that this must be a fluke of the measurements, something wrong with the observations.
Imagine the exact opposite answer that you're told to go and find. That is a big test of your scientific process, and 2 independent teams found the exact same thing.
We now know that the observations are absolutely secure. You can look at the universe in many different ways, and you see the same phenomenon.
In June 1998, the phenomenon was given a name: dark energy. At the turn of the millennium, a supernova hiding in Hubble Space Telescope data added to the complexities of the universe. 10 billion light-years from Earth, it was the oldest found up to that point. It revealed that billions of years ago, the universe's expansion was as physics had originally predicted. Dark energy was weaker than it is today. But before our Sun and all its planets were born, dark energy began winning a cosmic tug of war, pushing galaxies apart with more strength than gravity was pulling them in. The mystery of dark energy tantalizes cosmologists.
Well, I think the most exciting breakthrough in cosmology is the discovery that the universe is accelerating.
So what's causing it? Particle physics says that there is an energy of the vacuum itself. In fact, if that had been the dark energy, the universe would have ripped itself apart, probably within the first second of its existence.
It's often been described as the worst prediction or mismatch in history.
The European Space Agency's Planck telescope hunted for pieces of the dark energy puzzle, imaging the cosmic microwave background, the oldest obtainable light. This data in hand, astronomers calculated the exact composition of the universe. Dark energy comprises roughly 68% of all there is. Dark matter makes up another 27%. Only 5% of the cosmos is matter we can touch or light we can see.
But it's even worse than that. Most of the atoms in the universe will never even fall into a galaxy and reveal themselves. Bits that have made it into galaxies, that's basically 1% of all of the universe. But so far as we're aware, we're the only bit of the universe that has looked out and wondered about what a small bit of this universe we are.
To understand dark energy is to know the ultimate fate of the universe.
Our current understanding from dark energy is that we may be sailing off on an infinite journey of expansion, and the universe would last forever.
According to Einstein's relativity, that would be a runaway process where the expansion accelerates forever, more and more and more. Every star will at some point disappear, be infinitely far away from every other star. Every particle will decay eventually.
It looks like the universe will come to an end as a cold, dark, lonely place. So far better to be alive now than maybe in 40 billion years' time.
Missions to probe the mysteries of dark energy are already in motion.
There's different ways of measuring dark energy. We can see exploding stars, we can use clusters of galaxies, we can use how light bends around some galaxies.
At the Vera Rubin Observatory in Chile, astronomers are embarking on a decade-long venture to map the sky deeper than ever before, capturing 20 terabytes of data each night and cataloging 37 billion stars and galaxies.
And we use those results as independent cross-checks to the other probes. And we're trying to pinpoint that intersection of what dark energy could be now, which tells us what dark energy actually is.
Reality's greatest mystery is a test of patience.
For something that didn't exist in 1997 to 20 years later, having hundreds of people around the world trying to discover it just shows how big of a question it is to understanding the nature of our universe, the beginning of our universe, and the future of our universe.
We have defined the boundaries of our ignorance, and that's a very exciting place to be as a scientist.
Humanity's perception of reality is ever evolving.
Our view of the universe was dramatically different 30 years ago, 50 years ago, and 70 and 100 years ago. And it's amazing to think what our view of the universe will be in 10 years. How much more we discovered that we didn't know.
The vast, unknown reaches of the cosmos are begging to be explored.
95% of the universe is made up of completely mysterious dark matter and dark energy. We don't know what makes this up. We don't know if our picture of the universe is simply wrong.
It's a never-ending series of amazing discoveries about what is possible. It challenges our notions of who we are, where we come from, where we'll go to, how precious our own planet is. The study of the universe, to me, it impacts humanity on practically every level. And that's why I find it endlessly inspirational.
Our quest for answers is an essential part of what makes us human.
The universe created planets, created life, and created people who can ask all of these questions. That's just marvelous.
We hope to one day understand our place.
We are just a vanishingly small fraction of the universe, but so far as we're aware, we're the only bit of the universe that has looked out and wondered about what a small bit of this universe we are.